If we look at the flowchart in our workbooks that we started out looking at in this unit, trying to understand all the different parts of this, we can see that in almost all cases, in almost every outcome, we have some amount of competition with the E2 mechanism. This is a very common mechanism. It's very easy for the E2 mechanism to occur. And we're going to look at it by looking at this bromopropane. I've got the simpler version drawn up here, but in order to investigate the E2, the elimination, I need to be aware of where these hydrogens are. So let's quickly go over some factors in the E2 mechanism to see why is it so easily going to occur and what are the limitations to it, right? And remember we had a steric hindrance as a big barrier for the Sn2. We had carbocation stability as a big barrier for the Sn1, and we're going to have a barrier for the E2 as well. So first off, as far as substrates go, the E2 reaction is going to be able to occur with pretty much any substrate. So it doesn't matter how substituted it is. Where the Sn2 really needed that primary or secondary substrate, for the E2 mechanism, 1 degree, 2 degree, 3 degree are all okay. The one time it can't work is going to be in a methyl group. So it cannot work with a methyl substrate. And the reason for that is elimination reactions, by definition, are eliminating two groups in order to make a double bond. You can't have double bonds when there's only one carbon. So methyl groups are just out of the question. The second factor that we're going to look at that's going to help us compare the E2 and the E1 reaction is going to be like the nucleophile step in the Sn mechanisms. However, in elimination reactions, we're not adding a nucleophile. A nucleophile is specifically normally attacking something. In the elimination mechanisms, we're eliminating a functional group and a hydrogen. So we're actually really going to want a base. A nucleophile doesn't really matter. So I've got drawn up here base and nucleophile, just so that we know that we're kind of talking about the same aspect of the reaction. When we're looking at the substitution mechanisms that could occur, we're going to care about how nucleophilic is that thing. When we look at the elimination, we're going to look at how basic that thing is. But we're going to be looking at the same molecule. I'll hit that point again in a little bit, so if it's confusing now, that's okay. But just keep in mind that where the Sn cared about the nucleophile, the elimination cares about how basic that nucleophile is. And the elimination, the E2 mechanism needs a strong base. So that's one limitation. However, commonly, good nucleophiles are also strong bases. So as far as limitations go, that's not a very significant limitation. Solvents, well, for the E2 mechanism, pretty much any solvent is okay. So there's no limitation based on solvency. And then let's hit our rate law real quick before we talk about stereochemistry. The rate law, remember, the E2 is second order. That's where that 2 comes from. So the rate law here is going to be R equals rate constant times the concentration of a substrate times the concentration of the base. So increasing the concentration of either of these will increase the rate of that reaction. Finally, let's talk about the stereochemistry. This is going to be the limiting factor in elimination mechanisms, and it's going to tell us where a double bond is going to form. Elimination mechanisms are specifically going to be removing a functional group, so let's circle that. It'll be bromine on one carbon, and then on an adjacent carbon. So this one right here, we're going to be eliminating one of the hydrogens in order to form that double bond right here. So one of these hydrogens needs to get eliminated. Well, which one is going to be eliminated? Well, in the E2 mechanism, the hydrogen that is in an anti-configuration, so let's write that down. Stereochemistry required is anti-configuration. The anti-hydrogen is going to be eliminated. But what does anti mean? It means on the opposite side. So remember, these are three-dimensional molecules. I have my bromo group sticking up out of this page. So it is sticking up out of this page. And so I need the hydrogen on the opposite side of this. So that's going to be over here, okay? Now we're going to get to why that is in a minute. It's going to be because of the mechanism for the E2 reaction. But this bromine, notice the wedge is sticking out of the page. The hydrogen that gets eliminated is the one that is sticking into the page. It's always got to be on the opposite side. So anti-configuration means it's on the opposite side. So if I were to make a model of this bromopropane, it would look something like this. I've got 3 carbons, and I've got my bromo group sticking out towards us. When I say the opposite side, I literally mean on the opposite side of the molecule. So this hydrogen, that one right there is the one that would be removed. So it would remove this hydrogen and this bromine, and then a double bond would form between these 2 carbons. So that's what we mean by anti-configuration. So next we want to look at how do we model this mechanism? What's actually going on? What order are things going to happen in? So let's go ahead and draw out our substrate with all of the different pieces of the reaction present. Okay, so I've got my substrate drawn up here with all of the other business associated with it. I also went ahead and drew out the Sn2 mechanism that's going to occur at the same time. That Sn2 mechanism is going to use the hydroxide as a nucleophile. That nucleophile, that hydroxide is a very strong nucleophile, and that nucleophile is going to be attacking that carbon, which is going to steal the bond away from the bromine. However, hydroxide is also a very strong base. It isn't only interested in the carbon, it's also interested in the hydrogens that are attached to this alkane. Specifically, it's going to be able to take up this hydrogen right here. The reason for that is because this hydrogen is on the opposite side of that bromine. And when this hydroxide attacks that hydrogen, it sets in motion a cause and effect chain that will allow it to remove it. If it tried to attack a different hydrogen, it just wouldn't be able to go through all the steps necessary to pull it away. And it would hit it, maybe attach for a second, then pull away. And then it wouldn't have it. But if it attacks this hydrogen right here, let's draw our arrow, then this hydrogen can let go of its bond with the carbon. So this bond right here is going to go there. So that bond is not just going to disappear, it's going to then be pushed towards this other carbon. They're going to try and hold on to that negative charge between them. And then this carbon is going to be able to let go of another functional group. Now this bromine is perfectly stable, taking on a negative charge. It's a good leaving group. So this bond right here can go to that bromine. We wouldn't lose a bond to a hydrogen. That wouldn't make sense because hydrogen has terrible electron density. It wouldn't be able to hold on to that extra negative charge. It would try and give it away, and the hydrogen would just give it back. It would go, no, I do not want an extra electron. I am good here. So the only thing that can take this bond up is that bromine. So all of this has to occur at the same time. This oxygen attacks this hydrogen. That hydrogen gives up its bond to this carbon, which then tries to make a bond with this carbon. This carbon says, cool, man, I can let go of the bromine. And once that all happens, all at once, we get a water floating away. We get a double bond between these 2 carbons with this hydrogen left over and these 2 hydrogens left over, and we get a bromine floating around in solution. Now, all of these things are stable. So this is a one-way reaction. So because we have a strong base here, and we have an available anti-configuration. So we have a location for that strong base to attack and the available cause and effect chain necessary. We are able to form a very stable alkene. So let's redo this one more time, except let's get rid of all of these unnecessary hydrogens that really aren't going to be doing anything. Okay, once again, we've got our substrate drawn out. We've got it a little less busy this time. So I've got a bromo, I've got a hydrogen that's going to interact with a hydroxide. This hydroxide comes in and tries to snatch away that hydrogen. This hydrogen then gives up its bond with the carbon. That carbon reaches out to bond with this carbon, and this carbon says, I can totally do that, just let me get rid of this one bond with this bromine. The bromine accepts the bond, saying, hey, you know what, I'm totally fine with that negative charge. So we get 3 distinct arrows, 3 distinct handoffs that all have to happen at the same time. And then when those can all occur, we get a perfectly stable water, perfectly stable alkene, perfectly stable bromide. So when this reaction proceeds, it's going to have both the E2 mechanism and the Sn2 mechanism happening at the same time. And so really, we get 3 different products from this reaction. So the products we get from this reaction, from the Sn2 mechanism, we get an alcohol. From the E2 mechanism, we get an alkene, and we get our side products of sodium bromide. Plus, we're making a little bit of water. So let's look at one more example. I have here a bromocyclohexane along with an ion of ethanol. So this would be ethanol that lost its hydrogen, making it an anion. So really what this looks like is... So which type of mechanisms is this going to proceed by? Well, this would be a secondary substituted carbon. So I could have the Sn2, I could also have the Sn1, and considering this is going to be a pretty good base because of that oxygen right there, this is going to proceed according to the E2 mechanism. So let's consider the products that I would have with the Sn2 and the Sn1. They're going to make the same products because I haven't really established any stereochemistry here, and I'm not going to. So we'll just look at the Sn2 just to keep things straightforward. My Sn2 mechanism has this oxygen attacking from the backside. So it's going to make this attack, and this bond is going to be let go into the bromine. And I'm going to be left with an ether that is attached to a cyclohexane. I'm also going to be left with the bromide anion. So that was my Sn2 reaction. That's part of the products that I'm going to get. So I can draw those up here. But this reaction can also proceed according to the E2 mechanism. In that case, the ethanol ion, is going to attack a hydrogen near that bromo group. In that case, we need to keep in mind one of these hydrogens. Now, in reality, because these are equal, it could attack both sides. We would get both versions, but since that doesn't have any stereochemistry, it doesn't really matter. So, I can look at this according to the E2 mechanism. According to the E2 mechanism, this ethanol ion is going to attack this hydrogen instead of this carbon. So both of these events are occurring in the same reaction at the same time. We're just having different types of collisions. So this is going to attack that hydrogen. That hydrogen is going to give up its bond with the carbon. That bond is going to go between these two carbons. And finally, my secondary carbon, we call this the beta carbon, is going to give up its bond with the bromine. this results in the product of a cyclohexene, an ethanol, and a bromide anion. So in this reaction, I get a few different products. One is I get this ether. Two, I get this cyclohexene. Three, I get ethanol. And lastly, I get some bromine. So understanding these different reactions, these different mechanisms as an organic chemist is vital. Because if I was trying to just make some alkenes, I get a bunch of different side products that I now need to deal with. If I was just going into this trying to get some ethers, well, I now have some side products that I need to deal with that I'm going to need to find a way to get out of my solution. So this is very important to understand what side products are we going to be creating in our reactions.